Question 15a, the structure of an organic molecule can help predict the type of reaction that it can undergo. We've got the calculated structure of benzene suggesting that it should readily undergo addition reactions. So if we look at this structure here, which is the calculated structure of benzene, bearing in mind it's in resonance with an alternative model where the double bonds are altering in different positions, because we've got the double bonds, it should readily undergo addition reactions. But we know that that's not actually the case. Discuss two pieces of evidence, one physical, one chemical, which suggests that the structure on the last page is not the structure of benzene. So physical evidence is to do with the actual bonds, how long they are, how strong they are, what the bond order is. So any of these would be creditworthy. So the bond lengths or strengths are equal, as opposed to alternating, as was in the previous model. And the chemical evidence is to do with reactions. So they undergo substitution as opposed to addition reactions. They do not decolorize bromine water when we would expect alkenes to decolorize bromine water. They have an increased stability, more than we would expect if it was just the three double bonds. And the enthalpy is less than 3 times by 3 lots of double bonds. So we would predict from one lot of double bonds what the enthalpy would be for 3 lots of double bonds. And they actually don't match. So this would be our predicted value for cyclohexo-1,3,5-triene. 15b we haven't done because we haven't done redox. 15c, aldehyde being oxidized to a carboxylic acid. Outline the actual experimental procedures. So this bit here is to do with the act of synthesis. And how they differ. So aldehyde you have to distill immediately, whereas a carboxylic acid you conduct under reflux. In addition, I would put in that you have heat, you have complete oxidation, you have an excess of oxidizing agent in order to get it to go to a carboxylic acid. (15d) Empirical formula of an unknown compound. We know that it has got a C4H4O, and we know that its molecular ion peak is at 136. So the 136 peak tells us that this is the mass of the substance for the whole of the substance. Deduce, so figure out the molecular formula of the compound. So molecular formula is the actual formula as opposed to the empirical formula. The molecular formula is always going to be the empirical formula scaled up by 2, 3, 4, 5. You're just trying to figure out how many times you need to scale it. So the easiest thing to do here is to find out the mass of the empirical formula, C4H4O1. 12 is the mass of carbon, there's 4 of them. 1 is the mass of hydrogen, there's 4 of them. 16 is the mass of oxygen, there is 1 of them. If we add those up, that gives us a mass of 68. So if we take our 136 peak and we divide through by our 68, that gives us 2. So we know therefore that there are 2 lots of this molecule here. So we've got 8 carbons, we've got 8 hydrogens, and we've got 2 oxygens. You must state this to get the mark. The 2 wouldn't be enough to get the mark because it's asking you for the molecular formula of the compound. Question 16a. Organic molecules are visualised using 3-dimensional models built from kits, which you've probably used during the lab, and there's one pictured below. It's asking for 2 differences other than the number of atoms between the models of ethane and ethene as constructed from the kit. Now the key thing here is it's asking for differences, and it's even stating between ethane and ethene. So to get marks on this, you have to have comparative statements. Differences is implying that you are looking for a comparison between the two. So you have to have those either comparative statements or direct comparisons given by words. So for example, a double bond in ethene wouldn't get you the mark, but a double bond in ethene but not in ethane would get you the mark. Short bonds in the structure wouldn't get you the mark, but shorter bonds in the carbon to carbon in the ethene would get you the mark. So the shorter part here is what's important. Ethene has a planar structure, whereas ethane has a tetrahedral structure. Ethene has 3 domains, ethane has 4 domains. Both of these would be fine, but they would count as the same difference because they are both looking effectively at electron geometry. The other answer that you could have had is the rotation in the carbon-carbon bond in ethane is present, but in ethene, because it's a carbon-carbon double bond, you actually have a restriction of the rotation. So you've blocked the rotation that you have got in the ethene molecule. The next question is much easier than it first appears. So you're given a structure, you're asked to identify which of the circles shown represent the different atoms. So we've got a ball and stick model, substituted a pyridine molecule, doesn't matter if we don't know what it is, tells us what it's made from. Carbons, which have a mass of 12, hydrogens, which have a mass of 1, they're tiny, nitrogens, which have a mass of 14, kind of similar in size really, if we're looking at sizes of circles, to carbon, between carbon and nitrogen. So in this case, it's not going to be enough to look at the circles and decide that's nitrogen, that's carbon. So you need to think in this one about the bonds. Carbon is in group 4, it will form 4 bonds. Nitrogen will form 3 bonds. So when you're looking at your molecule, you have to look at how many bonds they form. Bromine is a huge atom, and chlorine is a huge atom, but it is smaller than bromine. It tells us here that the diagram shows a representation according to the atomic size, so that's how we know. We would assume it anyway, but it is giving us that information as well. It also tells us to exclude the hydrogens, so it's not necessary to label the hydrogens. A blank circle indicates that it would be a hydrogen. So here you get 1 mark if you've got the chlorine and the bromine. That's the easiest mark to get, bromine being the biggest and chlorine being big but not as big as bromine. So these are the 2 biggest circles and therefore our 2 biggest atoms. So 1 mark for bromine and chlorine. Then you get 1 mark for your 2 nitrogens and 1 mark for your 6 carbons. If you've indicated anything in these circles, you will lose marks. Here we know it's carbon because carbon's got 1, 2, 3, 4 bonds. Here we know it's nitrogen because it's got 1, 2, 3 bonds. So the carbons and the nitrogens, both of them are similar sizes. So here we have to look at how many bonds. Nitrogen because it's got 1, 2, 3 bonds. Carbon because it's got 1, 2, 3, 4 bonds. So that's how that question is done. The next question is simple. An advantage of using a computer-generated model as opposed to a ball and stick model to do with accuracy of measurements, so that you have really accurate representations of bond length and or bond angles. It means that they can be measured. So if you don't know the bond angles and you construct a computer-generated image, you can calculate the bond angles from those images. Better visualization. In particular, you can see rotational conformations. You can actually rotate all or parts of the molecule around and look how they relate to other structures, particularly useful for enzyme substrate complexes and biological molecules. And you can save it. So if you make a model, you can take a photograph of it, but then the photograph is 2-dimensional and you have to deconstruct your model. With computer-generated images, you can save them into a file and you can keep going back to them. 16D, pyridine, the molecule we looked at the top, like benzene, is an aromatic compound. Just outline, so very briefly, what's meant by aromatic. Now, yes, they do usually have an aroma, but that is not enough to get you the mark. Key thing about an aromatic compound is that it has a ring or it's cyclic. Either one of those is necessary for the mark, and it has resonance. So a ring with resonance or a cyclic substance with resonance, or you could say instead of resonance that you have a delocalized or a conjugated pi electrons. So that's what comes in benzene from that circle in the center of the cyclic substance. So the ring and resonance or ring and delocalized electrons. Aroma is not incorrect, it just doesn't get you the mark. Question 17. This question is about the reactions of halogenoalkanes. Compare and contrast. So this again is a comparative narrative. You have to give indications of potentially how they are different, and sometimes ER statements might become useful in these types of questions. First thing that I would do when faced with this question is to draw the 2 structures. Compare and contrast the mechanisms. Mechanisms, we know that means curly arrows involved. How does it progress? Do we have intermediates? Do we have transition states? I've started off, as I mentioned, by drawing the structures, 1-chlorobutane and 2-chloromethylpropane up here. Then when I look at them, I think, okay, well this one's primary and this one is tertiary. Primary and tertiary, therefore, are going to undergo two different types of mechanism when they react with sodium hydroxide to form alcohols, and we're looking for two similarities and one difference. Two similarities, both of them undergo heterolytic bond breaking. In both of them, the Cl- leaves. Both of them are nucleophilic substitution. Yes, they do both produce an alcohol, but that wouldn't get you the mark. That's not credit worthy. A difference could be anything linked realistically to the mechanisms that take place. So we either have Sn1 or Sn2 mechanisms. Sn1, you'd need to tell me what it was for, so it was for the tertiary. It proceeds in two steps. It has an intermediate, it's unimolecular, and the concentration of the OH- ions is unimportant for rate. Whereas for your Sn2 mechanism, for your primary halogenoalkane, it's bimolecular. The OH- is important for the rate, and it proceeds in one step and takes into account a transition state as opposed to an intermediate. So these would be fine to get the mark, or uni and bimolecular, or these, or these. So there's a variety of ones there that you can choose from. 17b, outline why the rate of reaction of similar bromo compounds is faster. So that's saying if these were bromo compounds, why would they react faster than they do when they are chlorine? Now, in this part of the syllabus, there are two factors that we've considered. So there is strength and there is polarity that both contribute or potentially have the ability to contribute to a rate of reaction. Where we've got a CCl bond, we know that this is the stronger bond. We know that this is a stronger bond because we've learnt it. We've learnt it in class. We can look at it in the data booklet, and we can get that information also. So because it's stronger, it's harder to break, harder to react. The CBr bond is weaker than the stronger CCl bond. And you notice here, compare and contrasting, because it's looking at differences, faster, then I'm going to use stronger and weaker. The weaker CBr bond is easier to react because it's easy to break. The other factor, which is not relevant to this question, is to do with polarity. CCl has more electronegativity difference. If it's more electronegativity difference, then it has a greater polarity. If it has a greater polarity, we would expect it to be easier to react. The CBr bond has less electronegativity difference, and therefore we would expect it to be harder to react. Now, the question's asking us why the bromo compound is faster. Well, out of the two pieces of information we've just looked at, the one that's going to allow this to be true is the fact that we've got a weaker bond, which makes it easier to react, and therefore it would be faster. So the answer, the reason, is that the CBr bond is weaker than the CLC bond. This bond is weak, would not get you the mark. You have to have the comparison. State the organic product of the reaction between 1-chlorobutane and aqueous sodium hydroxide. So here I'm just indicating this is my structure, this is my chlorine, that's coming off, and this is going on. That helps me give this as my structure of my product, and if I were to name it as butan-1-ol, butanol would not get you the mark, butan-2-ol would not get you the mark. This would get you the mark, however. 17d suggests how this product, i.e. this product, could be synthesized in one single step from butanoic acid. Now we know that alcohols can be oxidized to aldehydes, which can be oxidized to carboxylic acids. Carboxylic acids can be reduced to aldehydes and be reduced to alcohols. This is two steps, two stages. For this to happen in one stage, for this reduction to happen in one stage, we have to use this specific chemical. If you were to use an alternative, or you were to state an alternative, some students often state sodium tetrahydroidoborate. That would not give you the mark here, because this one allows the reduction to be much stronger, which is why it's synthesized in one step as opposed to one step to aldehyde and one step to alcohol. And question 17e, deduce the name and class of compound formed when C reacts with butanoic acid. I've got an alcohol from C, I've got a carboxylic acid from here. Alcohols and carboxylic acids give me an ester. And there is a beautiful picture of my yoga mat.